I guess we're going to go ahead and get started. Good afternoon, ladies and gentlemen. Welcome to this third and last session of biomass conversion to chemicals. I am Burjubaya. I am with BASF Corporation up in New Jersey in the research division. My co-chair here is Dr. Jim Domestic from University of Wisconsin. We're going to have 4 presentations today. We're going to start with a keynote lecture by Dr. Fukuoka of Hokkaido University from Japan. His keynote lecture is titled Conversion of Cellulosic Biomass into Chemicals by Heterogeneous Catalysts. So without further ado, I would like to invite Dr. Fukuoka for his keynote lecture.
Thank you, Dr. Bayram, for kind introduction. It's my great pleasure to give a keynote lecture at this meeting. Today I'm going to talk about our recent results on the conversion of cellulosic biomass by heterogeneous catalysts. In this presentation, first I will talk on our motivation of our work, reviewing some of the early studies and technical issues. Then I will show you some of the results of hydrolytic hydrogenation of cellulose to sorbitol. Then I will focus on the hydrolysis of cellulose. I will show you our new carbon catalyst, its preparation, characterization, catalytic performances, and a proposed reaction mechanism. Finally, I will make a brief summary and talk about future plans. Our goal is conversion of cellulosic biomass into platform chemicals, such as glucose, sorbitol, and xylose, by heterogeneous catalytic processes. And the lignocellulosic conversion is mainly performed by the enzymatic processes or sulfonic acid or thermal reaction conditions. But recently, people are interested in the application of heterogeneous catalysts to these reactions. In our work, lignin conversion is another topic, and I will not mention it in this talk. And after synthesizing of the platform chemicals, next step is conversion of the platform chemicals into value-added chemicals, which will be performed by the catalysts or the enzymatic processes. And our interest has been in the catalyst design for the depolymerization of cellulosic materials, in particular the conversion of cellulose. Okay, let me first mention that the motivation of our work. As early studies, Russian chemist Dr. Marandin reported in 1957 the hydrolytic hydrogenation of cellulose to sorbitol by using the sulfonic acid and the ruthenium carbon catalyst. And almost 50 years later, we reported that the sulfonic acid is not necessary. Just a supported platinum catalyst on the alumina promoted formation of a sorbitol, because supported metal catalysts also promote that hydrolysis step. But later we found that the transformation of alumina, the gamma alumina, to a bromide in hot water conditions. So recently, our preference is that the use of carbon as a support. Okay, and Dr. Hara of Tokyo Tech reported hydrolysis of cellulose, depolymerization of cellulose by using sulfonated carbon. And also other groups reported cellulose hydrolysis by using sulfonated reagents such as amphotericin or natrium. But their main product is polymosaccharide. So as technical issues, we observed that the first technical issue is a significant leaching of sulfonic acid at high temperature. in water. So as far as we do the reaction, we observe that the leaching of the sulfonic acid. So the sulfonated materials shows low durability in hot water. So finally, I decided not to use sulfonic materials as a catalyst. And the second issue is that this reaction is a solid reaction between the solid substrate and solid catalyst. So you have low contact between the solid and solid. So we need to increase the contact between the solid substrate and solid catalyst. And the final issue is that we need to increase the one-pot yield of glucose. So improvement in this study includes that we have developed a new catalyst, alkali activated carbon, as a durable catalyst, even under high temperature in water. And mixed milling method improved the contact between the solid substrate and solid catalyst. And finally, the diluted hydrochloric acid greatly improved the one-pot yield of glucose. Okay, let me first mention that the recent results on the hydrolytic hydrogenation of cellulose to sorbitol. We used ruthenium-containing bimetal catalyst, and here the support is BP2000, typical carbon black material. And as among the tested catalysts, we found that iridium-ruthenium catalyst shows good yield of sorbitol, 56% and mannitol 5%. And the selectivity based on carbon is 87% for hexitol compound. So very recently, we also found that the hexitol yield is increased to 86%. Here the sorbitol 79 and mannitol 7, with mixed milling of cellulose and catalyst. Now I will show you the details of mixed milling method later. Now also other groups reported higher yield of hexitol 80%, 90% by using the soluble catalyst and by using the mixture of soluble catalyst and solid catalyst. Okay, we applied the hydrolytic hydrogenation reaction to real biomass conversion. Here we used the corn, rice straw, corn cob, and silver grass as a real biomass. And our pretreatment method is simple. Just washing the powder in boiled water to remove cations and just drying. And in these reactions, our catalyst is platinum BP2000. BP2000, and the reaction temperature is 190 degrees Celsius. Initial hydrogen pressure 50 bar in water media, and the reaction time is 24 hours. The silver glass contains cellulose in 39 weight percent, and hemicellulose in 22%, and lignin 16%. But after the reaction, you observe that the formation of sorbitol in 10% and 16% xylitol and 5% rhabitol. So that under the reaction conditions, the hemicellulose part is completely converted to sugar alcohol, so the main product is xylitol. And also that we found that the lignin is inactive. Lignin does not affect the catalytic result. Okay, let me move on to the hydrolysis of cellulose to glucose. This reaction is important because glucose is a very useful precursor to synthesize ethanol, lactic acid, and 5-hydroxymethylfurfural HNF, and they are easily converted to fuel and polymers by using the current processes using enzyme and catalytic heterogeneous catalyst. But as I mentioned, the stopping the reaction at glucose is difficult because glucose conversion is also easy processes. So that the target is a selective hydrolysis of cellulose to glucose. Okay, here is first we try to use the supported metal catalyst because this ruthenium carbon catalyst was a good catalyst for the hydraulic hydrogenation of cellulose to sorbitol. And here our catalyst was the ruthenium CMK3. CMK is a mesoporous carbon, replica of SB15. So here the red bar shows that the yield of glucose, and the blue bar is yield of oligomers, and gray bar is the yield of byproducts such as HMF, fructose, mannose, and riboglucosan, and total height corresponds to the conversion of cellulose. As you can see here, the 10% ruthenium CMK gives 31% of glucose, 5% of oligomers. But by decreasing that metal loading to 8% ruthenium, give almost the same glucan yield. And finally, metal-free CMK give also that glucan yield of 38%. This was a trigger for us to study the catalytic functions of carbon materials in detail. So here the metal is not necessary. Okay, here you can see that the preparation of alkali activated carbon K26. The precursor is a typical coke powder, and this coke powder is mixed with the powder of potassium hydroxide, and then the mixture was heated under nitrogen at 700 degrees Celsius for 2 hours. Then the washing, neutralization, and washing, filtration, and drying. Here is the photo of K26. Typical black powder. And BET surface area is 20 to 170 square meter per gram. And the titration with base shows that the concentration of carboxylic acid is 270 micromole per gram, lacton 310, and phenol 310. Then in this ammonia TPD for K26, you don't have any L peak or H peak in this figure. So that we found that there is no strong acid site on the surface of the K26. Okay. Here is the Raman spectrum of K26. You can see that the D band and the G band, and the D band is relatively bigger than the usual graphitic materials. And so this means that relatively high concentration of the defect site. And it is roughly estimated that about 10% of carbon located at the defect site. So we expect that oxygenated functional groups locate at 10% defect carbon site. Okay, here are our reaction conditions. We used ball milled Avicel as a cellulose material, and weight is 324 milligram. And catalyst, carbon catalyst 50 milligram, and water media 40 milliliter. And we used that batch type autoclave made of Hustler as a reactor. Here you can see our reaction temperature profile. First, the temperature increased from the room temperature to desired temperature, say 180 degree or 200 degree in 15 minutes. Then they keep the reaction temperature for 20 minutes or in some cases 0 minutes to avoid the further degradation of the glucose, and quickly cool down to room temperature. So total reaction time is 40 or 60 minutes. Here are the results of a screening of a carbon catalyst. This is a result of the non-catalyst case. Even without the catalyst, the cellulose conversion is about 30%, and glucose yield is 5%, and oligomer yield is 15%. This is probably catalyzed by in-situ generated proton proposed by Dr. Liu. And as you can see here, by using the various kind of carbon materials, the conversion and glucose is very different. For example, when you use CMK as a catalyst, the conversion is 50%, and glucose yield is 12%, and oligomer is 25%. But if we use the K26 alkali-treated carbon as a catalyst, the cellulose conversion is 60%, and glucose yield is 1-pot glucose yield is 36%, so that the selectivity of glucose is 60% based on the converted cellulose. And we also observed that the active catalysts have more amounts of oxygenated surface functional groups. Okay, and next step is a mixed milling method. We apply mixed milling method to improve the contact between the solid cellulose and solid catalyst. This method is very simple, just mixing the cellulose powder and carbon catalyst powder. And the weight ratio is kept at the reaction ratio, so say 10 grams of cellulose and 1.5 grams of carbon catalyst. And they are just mixed in the pot and milled for 48 hours at room temperature. And here are the SEM image of mill sample. This is the cellulose before the milling, and here you can see that the smooth surface of the cellulose, and even after the milling processes, the surface of the cellulose is comparatively smooth. And the particle size of K26 carbon catalyst is smaller than the milled cellulose particle. And in this mixed milled sample, the surface is round. So in this enlarged figure, you can see that some smaller particles of carbon are located on the surface of cellulose to make the surface of cellulose round. So we think that smaller carbon particles are located, or in some cases buried, on the surface of cellulose to make good contact between the cellulose and the carbon materials. Okay, here are some results of characterization of the mixed mill sample. In these XRD patterns, both mixed mill sample and individual mill sample show the similar broad peak due to amorphous cellulose. Before that milling process, you have that sharp peaks of crystalline cellulose, as shown here. And in the carbon NMR, we have the separated peak of C4 carbon, as shown here, at 80 to 90 ppm. And by analyzing that peak area, it is estimated that crystallinity of cellulose is below 5%. And degree of polymerization of cellulose, mixed milled cellulose is 690, and individual milled cellulose shows that the degree of polymerization of 640, so almost the same. And the median diameter of the mixed milled and individually milled samples shows that 35 micrometer. So, and also we don't observe any mechanocatalytic reaction, so no soluble products after that mixed milling sample. So just mixed milling makes better physical contact between the cellulose and catalyst. Okay, here is a proposed structure for solid-solid interaction, and smaller activated carbon particles are deposited on the cellulose surface, and the absorption is probably enhanced by the hydrophobic and the hydrophilic interaction. So hydrophobic interaction is a CH-I interaction between the graphite surface and also the actual CH actual phase of cellulose. And the second hydrophilic interaction is H hydrogen bonding between the sugar OH groups and the surface oxygenated functional groups. And crystalline cellulose turns to amorphous and hydrolysis gets started. Okay, here is the results of a catalytic reaction by using the mixed metal sample. Here, in these reactions, our reaction conditions is 180 °C in water media for 20 minutes. And as you can see here, when you use individual meal sample, the cellulose conversion is about 18%, and glucose yield is 3%, and oligomide yield is 10%, just slightly improved compared with the blank case. But when you use mixed metal sample, the conversion is greatly increased to almost 90%, and glucose yield is 20%, and oligomide yield 17%. This is very striking effect of mixed milling method in the presence of alkali activated carbon catalyst. So mixed milling and K26 catalyst greatly increase the catalytic performances. Then we added the diluted hydrochloric acid in place of pure water as a reaction media to convert this oligomer part to monomer. So we use that diluted hydrochloric acid, the concentration is as low as 0.012%, and pH is 2.5. As you know that typical stainless steel is tolerant of pH 2 to 3. So now that 1 pot glucose yield is 88%, this is one of the highest yield in 1 pot reaction by using the heterogeneous catalyst. Okay, we checked the use experiment of our carbon catalyst. And after the first catalytic run, the recovered solid contained the catalyst and unreacted cellulose. And then we added the fresh cellulose to compensate the consumed cellulose, and then mixed milling and the second reaction in diluted hydrochloric acid. And in this reaction, we used a high concentration of cellulose, 200 grams per liter, for the potential, for the future application of cellulose conversion. So, as you can see here, that the conversion, cellulose conversion is about 90%, and glucose yield is 17%. This corresponds to the glucose concentration of 13 to 14 weight percent. So you can reduce that energy for the evaporation of water by using the high concentration of this glucose solution. Okay, so as far as we do that reaction in 4 times, the conversion is about 85 to 90%, and the glucose yield is 70 to 75%, but actually the conversion of glucose is slightly decreased. This is maybe due to the formation of polymeric byproducts such as fumin. So we need to overcome this slight decrease of conversion and glucose yield in the future. Okay, we applied our method to the saccharification of real biomass, bagasse pulp. After mixed milling of bagasse pulp and the carbon catalyst, in this reaction we used the commercially available BA50 from Ajinomoto. This is a steam-activated carbon. So we wanted to eliminate the alkali treatment to reduce the cost of the catalyst preparation. Anyway, this carbon material shows good concentration of satisfactional groups, so we used this material as a catalyst. In the first step, the hydrolysis was tested in diluted hydrochloric acid at 180 degrees Celsius for only 1 minute. Then you have xylose as a main product by the conversion of hemine cellulose. And then we raise the temperature to 210 degrees for 2 minutes. Then switch it to the conversion of cellulose to glucose, and glucose is about 70%. And total yield of hextol is 80%, and main product is glucose, and the total yield of pentose is 90%, and the main product is xylose. Okay, let me move on to the mechanistic study of cellulose hydrolysis. First, we wanted to correlate the catalytic activity with the satisfactional groups. So we used the heat-treated sample of K26. Heat treatment was done at 400, 600, 800, and 1000 degrees centigrade in helium for 2 hours. But as we expected, that the concentration of functional groups decreased by for the heat treatment sample, and also we observed a decline of the conversion and the glucose yield. So we suggest that the catalytic activity is closely related with the concentration of satisfactional groups. In these reactions, we think that the lactone can be converted to carboxylic acid and phenol under the reaction conditions at room temperature, at high temperature in water. Then we conducted a model reaction, Cellulosic hydrolysis. Here the Cellulosic is a model of cellulose, and these organic compounds are the model compounds of surface of activated carbon. And reaction condition is 170 degrees for 10 minutes. And as you can see here, phenol or benzoic acid are inactive, but the salicylic acid bearing carboxylic acid and OH groups hydroxylate in ortho position shows very high turnover frequency, 28 per hour. But by using the meta or para hydroxy benzoic acid, we observe very low catalytic activity. So this means that the ortho positioning is very important. Among ortho positioning, so when we use chlorobenzoic acid, we observe that the less catalytic activity than the salicylic acid. When we use the phthalic acid, or that 2 carboxylic acid in ortho position also shows very high activity for the Cellulosic hydrolysis. So we think that we have 2 important factors. First is the pKa, because this is closely related to acid catalyst reaction, and the second is the positioning of the functional groups. Okay. We also conducted a kinetic study by assuming that the typical second order reaction, first order for Cellulosic concentration and the first order for the catalyst concentration. As you can see here, that the active salicylic acid and the inactive also chlorobenzoic acid shows almost the same slope. The activation energy will be similar. So actually, the activation energy, apparent activation energy for the active and inactive organic compounds are almost the same, in the range of 110 to 120 kilojoule per mole. But frequency factor is very different. frequency factor for salicylic acid is 74, which is 5 or 10 times higher than those of other active or inactive catalysts. So the frequency factor is important in this reaction. And then we measure the NMR to get information of the interaction between the cell bios and the organic compound. They are diluted, dissolved in the DMSO, and we take that proton NMR at room temperature. As if we don't, add organic compound, cell bios shows two kinds of proton peaks, OH peaks and CH peaks, as shown here, very sharp. But by adding the organic compounds, only OH groups, proton of OH groups broaden. And in addition of salicylic acid, you observe a very broadening of the OH peaks. This means that the fast exchange of the proton between the salicylic acid and OH protons of the cell bios. But still the CH peaks is sharp, as shown here. So the CH proton is not involved in this proton exchange. And by calculating that reaction rate of that proton exchange, the reaction rate is 180 per second for the salicylic acid, which is 10 times higher than those of other organic compounds. So salicylic acid specifically interacts with cell bios by exchanging proton with OH groups. So here is the most stable model structure of that interaction between the salicylic acid and cell bios. The phenolic groups interact with the OH groups at the C6 position, and then the carboxylic acid get access to that glycosidic bond as shown here. So hydrolysis can get started. Here is our proposed reaction mechanism. First, the phenolic groups interact with the OH groups of the sugar molecule, say cellulose OH groups, and then carboxylic acid get access to glycosidic bond to cleave it, and then you have cation and anion, carboxylate, after the cleavage of the glycosidic bond. Then water neutralizes the cationic sugar part and carboxylate. Then the dissociation of the remaining sugar part regenerated the surface functional groups. A similar synergistic effect of the surface functional groups already reported by other groups. Dr. Hara reported that hydrogen bonding is formed between the phenolic groups and the hydroxy group of cellulose, and then so the carbon adsorbs the cellulose. And as shown in the previous lecture by Dr. Chan, Dr. Katz's group reported that once covalent ether bond is formed, the glycosidic bond of immobilized cellulose activated by free OH group on the surface of alumina or silica. Okay, so that our reaction mechanism is quite similar to the mechanism for enzymatic hydrolysis of cellulose. In the enzymatic reaction, in the retention type reaction mechanism, you need the carboxylic acid and conjugated carboxylate on the enzymatic surface. This base carboxylate attacks the C1 position of sugar, and then the water attack again to give beta aroma of sugar. This is a retention mechanism. And in the inversion mechanism, first the carboxylate attacks water, and then the OH attacks to the C1 position to form that alpha atom as a product. This is the inversion mechanism. But you need the coexistence of a carboxylic acid and a carboxylate in the enzymatic process. So you need a careful control of reaction solution, pH of a reaction solution by using buffer. So let me compare that our activated carbon catalytic reaction and the enzyme. So the activation energy for enzymatic process is about 30 kilojoule per mole, but our activated carbon shows that activation energy is 110 or 120 kilojoule per mole. But our catalyst durability is quite high compared to the enzyme, and we can apply a wide variety of conditions in the heterogeneous catalytic reaction. And at high temperature, we can have high reaction rate. But still, the selectivity by enzymatic process is very high, almost 100%. And right now, our catalyst shows that selectivity of 88%. And as you know, the cost of enzyme is high, but our activated carbon is cheap. Okay, let me summarize my talk. Supported metal catalyst works as a catalyst for the hydraulic hydrogenation of cellulose to sorbitol, and alkali activated carbon, K26 hydrolyzed cellulose, and mixed milling greatly increase as 1-pot glucose to up to 88% in the presence of diluted hydrochloric acid. Bagasse pulp as a real biomass is selectively hydrolyzed to C5 and C6 sugars, and we propose that the neighboring carboxylic acid or OH groups on the activated carbon are catalytic active site. And future work includes the estimation of the hydrophobic interaction between the cellulose and the carbon catalyst. And the second topic is the hydrolysis of crystalline cellulose. As far as we do that, artificial catalyst can hydrolyze amorphous cellulose. The only enzyme can hydrolyze cerebrial hydrolase can hydrolyze crystalline cellulose, but we wanted, our future work is trying to hydrolyze crystalline cellulose by using the artificial catalyst. Finally, I'd like to thank my co-workers, in particular Dr. Hyokas Kobayashi, Dr. Kamanoya, and Mr. Yabeshita, and Shu Odenko. And finally, I'd like to thank financial support from JSP. Thank you for your kind attention.
Thanks for your wonderful talk. I'm Cheng Wen, come from University of South Carolina. I had one question about the acid side. You said that the carboxylic acid side is the active site for the hydrolysis, but you didn't see any acid side from the ammonia TPR. How could that happen?
Your acid site on the other acid site, you mean?
No, just the acid side. You didn't see any desorption peak from the ammonia TPD?
Ammonia TPD? Yeah, we did it. We didn't observe any weak acid site or strong acid site in the ammonia TPD profile. So this is a result of ammonia TPD. So no L peak or H peak appeared in the ammonia TPD. So that carboxylic acid is very weak acid site.
Let us take Dr. Fukuoka once more.